Okay, so we are at chapter 4 here. No, yes, 4. And in this chapter, last time we talked about geometry, basically. We talked about two types of geometry. One, again, is the electron pair geometry, which describes really the sort of three-dimensional arrangement around the central atom of the electron pairs, be it bonding pairs, non-bonding pairs, how they are arranged. We also talked about molecular geometry, or sometimes referred to as the shape of the overall molecule. And that describes, really it's influenced by the type of electrons that are present around the central atom. As we saw in certain cases, both the electron pair geometry name and the molecular geometry name are exactly the same. And those are cases where pretty much the only type of electrons around the central atom are bonding electrons. So those bonding electrons are obviously bonded to atoms. So as those bonding electrons move, which is sort of the basic principle of the geometry part, which is that electrons are negatively charged. So they really do want to sort of get as far away as possible from each other since they are sort of like charged. But obviously they can't escape because they're within a bond or within that atom. So as they start to move and as they have bonds there, the atoms will start to move. So that is why the electron pair geometry and the molecular geometry are the same for situations where you have just bonding electrons near each other. It's really when we start to introduce non-bonding electrons around the central atom that we do start to see a change, and it's the change in the overall shape of the molecule, the molecular geometry. The electron pair geometry still remains the same based on how many electron pairs there are, but in the case of having non-bonding electrons present, they are not really attached to an atom in that case, so they have a little bit more room for movement. And there is sort of a level of acceptedness of electrons being near each other. Sort of the most acceptable sort of situation is bonding near bonding electrons. The next sort of worst situation is actually bonding near non-bonding electrons. And the worst of all situations is sort of non-bonding electrons near non-bonding electrons. And when we start to get situations where we have non-bonding electrons near bonding electrons, they're able to move a little bit more because they're not really restricted by that extra atom that they bond to that we have in sort of the bonding situation. And we do end up getting some different molecular geometry names for those guys and a little bit different bond angles because of that little bit more freedom that they have that occurs. We get even more sort of freedom and more sort of tweaking of the overall shape of the molecule when we sort of introduce non-bonding electrons and other non-bonding electrons being there. Again, they're both not tied to any type of atom that's present, so they're able to really sort of spread out a little bit more from each other. The best way to do it, as we talked about, is sort of, just memorization. And really what you want to look for is always the central atom is always the most important thing. As we talked about, there may be situations where there's more than one central atom. So you could do the geometry for each central atom separately from each other. But it's really two things that you should count is basically the total number of electron pairs. And again, it doesn't matter if they're bonding, which are lines in Lewis structures, or dots, which are non-bonding electrons. When we do count electron pairs, we are also treating double bonds and triple bonds as only one electron pair. So effectively, they are acting as sort of one electron pair. And you want to count up how many bonds there are. And same thing with the bonds, double bonds and triple bonds count as only one bond as well. So again, when you're doing geometry, that's sort of the situation there. We got into a little bit at the very end there about hybridization, which is sort of an idea of bonding where, we kind of take atomic orbitals like S's and P's, maybe D's as well, and really kind of mix them together and make these hybrid orbitals. The sort of advantage of this idea of bonding is the idea that if you just take the atomic orbitals like an S and a P orbital, they are of sort of different shapes, there are different energy levels. So it makes them an awkward sort of bonding and stuff like that. Through the use of sort of the idea of hybrid orbitals, what we're creating are orbitals that basically have the same sort of size and they're at the same energy. So it allows for better sort of overlap and bonding to occur. I think we talked about the first one there, which was an Sp hybrid orbital. And that is really a combination, again, of an S and a P orbital. Excuse me. And remember that these are, again, our atomic orbitals. And it is the number of atomic orbitals that we really do combine that gives us sort of how many hybrid orbitals that we would make. So in this particular example, we would make something like 2 hybrid orbitals, which again would be sort of the same size, also the same sort of shape. Because we are hybridizing p orbitals, the p orbitals do have, right, 3 different p orbitals, the px, the py, and the pz. So if we were doing SP, we're really just hybridizing this first one, which also leaves us, as we talked about there, some unhybridized regular sort of p orbitals that are still there, that are unhybridized in this case. We also talked about, and as we will see as we go through the other ones here, really hybridization is linked to electron pair geometry. So the hybridization here is linked to the electron pair geometry. And really sort of the simplest way to look at it is, frankly, that is like 2 letters. And that would be like 2 electron pairs, and that would be the linear geometry is what we typically see with the SP hybridization. Any questions on that? Okay. Then let us continue on and talk about the next one, which is an Sp2 hybridized orbital. So in this case, we're taking S atomic orbital, and we're actually going to take 2 of the 3 p orbitals here, and we're going to hybridize them. As you can sort of see here, we have our s orbital. Here's sort of 1 p orbital hanging around this way, and 1 p orbital kind of coming out there in front. And again, they're going to hybridize and make these sort of lobes here, which are these hybrid orbitals, which, as you can see, is sort of the same size. And because we're taking an S really, and we're going to take 2 of these P's, that is going to result in 3 Sp2 hybrid orbitals happening. Again, the number of hybrid orbitals that you make is equal to the number of atomic orbitals that you combine. That, as you can see here, will leave us a unhybridized p orbital, which is actually the pz orbital. That would be unhybridized in this particular case. Now, Sp2 is frankly 3 letters there. If I write it right, there we go. That is 3 of them. And 3 electron pairs, when we talk about electron pair geometry, is the trigonal planar geometry that goes with that. And that's what we see here. It makes that triangle, as you can see here, which is 120 degrees. So we get the trigonal planar geometry here. So anything that you look at, if you draw sort of a Lewis structure of, and you count up the electron pairs like you're doing geometry, and you just count 3 electron pairs, that particular atom there in the center would be Sp2 hybridized by just looking at that. Any questions on that there? So if we look at an example of that, which would be BF3 here, again, BF3 is an exception to the octet rule. It's an incomplete octet. Boron is 5, which would be 1s2, 2s2, 2p1 would be boron there. And it is these 3 valence electrons here that we see pictured over here to start with. So this is boron, sort of valence electrons that are present. As we talked about before, always sort of in the hybridization process, what we will see is a promotion of a lower electron up to a higher one. And just like we talked about with orbital diagrams, it will then go to the individual orbitals first, just like they feel like an electron configuration. So it would find itself over there in the py sort of guy. We would get this promotion of electron, and then it's going to be these 3 guys here that are going to go through hybridization. And once again, as I mentioned on the previous page there, we have 3 hybrid orbitals that would be made. And we would have 1 unhybridized p orbital, which in this case would be the pz orbital, which would be unhybridized in this particular case. Each of these guys, right, have basically 1 electron in their hybrid orbital, which means they could then go bond with, frankly, the fluorine in each of these cases and share an electron there, and make the 3 bonds that we see in something like BF3 in this particular case. Again, if you remember, it looks like this basically. So fluorine having the 2p5 going to share, sort of electrons into here, going to allow it to complete really sort of its octet and make the bonding that occurs in that case. Any questions on that one? So that is Sp2 hybridization that occurs. The next sort of hybridization that could occur, as you can imagine, is we're going to pretty much take all three of the p orbitals there and the s orbital and going to hybridize those guys together. And if we do that, we will get what is known as Sp3 hybridization. And Sp3 hybridization, as I just mentioned, pretty much once again, we got our s orbital, and kind of hard to see, but there's one p orbital, two p orbitals, and three p orbitals sort of happening here. So we're going to take all those guys, and because we are hybridizing the s orbital and once again all three of these p orbitals, that is 4 individual atomic orbitals, that will result in 4 equivalent Sp3 hybrid orbitals being made. And again, they do all have sort of the same shape. Once again, we could tie this to our electron pair geometry, just really counting letters there. So that's 1, 2, 3, 4 electron pairs, basically. 4 electron pairs is tied to the tetrahedral electron pair geometry. So once again, if you sort of draw your Lewis structure and you see 4 electron pairs around that central atom that you want to apply hybridization to, that will tell you that it is Sp3 hybridized here. That also means it has the typical tetrahedral bond angle of 109.5 degrees happening here. In this case. So an example of that is one that we saw previously, which is methane. And once again, looking at carbon here, carbon 1s2, 2s2, 2p2. Carbon has these 4 valence electrons, which is what we see pictured up here. And this is carbon's valence electrons. Once again, we're going to get that promotion of that electron sort of up to the empty p orbital there. That is going to result in all these guys basically going through hybridization. So once again, since we are going to hybridize all 4 of those atomic orbitals, that will result in a 4 equivalent Sp3 hybrid orbitals. And once again, if you look at the Lewis structure here, that's going to allow each of these hybrid orbitals in carbon to basically make a bond with a hydrogen in each of those cases. So we would get a bond to a 1s hydrogen orbital, and hydrogen, hydrogen, and hydrogen. Again, allowing for better overlap as all those hybrid orbitals, again, are at the same sort of energy level and good sort of completing the octet, in this case, actually completing the 2 electrons that are needed for hydrogen in each of those cases. Any questions on that there? So what we see here is, in these couple examples, our hybridized orbitals are involved in bonding, and they don't always have to be sort of involved in bonding that occurs. They could be involved in some of the non-bonding that happens. So in general, we talk about lone pairs as well as bonding electrons can occupy a hybrid orbital like NH3 and H2O. Bonds in which there is head-to-head overlap of these orbitals are what are referred to as sigma bonds. So sigma bonds are sort of like single bonds, if you will, and it's a result really of, frankly, the orbitals just going straight at each other and basically running into each other, and that overlap that occurs as they sort of come together. Hybrid atomic orbitals result again in stronger bonds than both sort of unhybridized orbitals. So let's take a look at NH3 here. So we take a look at NH3. For example, here, we look at our nitrogen, which is 1s2, 2s2, 2p3. So nitrogen here has basically 5 valence electrons, the ones in the box. And if we sort of draw our little diagram here for nitrogen to sort of what's going on, we would start with our 2s orbital that has the 2 electrons in it. They would also have, obviously, our 2p orbitals, which has 3 electrons in it. And if we draw the Lewis structure here for NH3 like we've done before, if we count up the electron pairs around the nitrogen in this particular case, how many total electron pairs are there? Around the nitrogen, there are 1, 2, 3, and 4 electron pairs. So remember, you count dots, lines, doesn't really matter. 4 electron pairs, frankly, just straight from the Lewis structure, the hybridization should be. It would be Sp3 hybridization. So let me just show you a very simple way you can figure that out, which is, frankly, there's an S, there's 3 p orbitals, there's like 5 d orbitals. We just counted 4 electron pairs, so you do this, 1, 2, 3, and 4. That's an S and 3 p's. That would be Sp3 hybridization, is what we would expect. So what that tells us in this particular case is we are going to get a promotion of this electron here. It's going to go up to our p orbitals, but just like we did with electron configuration, there's already an electron in each of the p orbitals, which means that promoted electron will actually end up over here in the first guy. And after that promotion there, we will end up with these electrons like this. We're going to then hybridize all of these guys here. As we know from our Sp3 hybridization, that is going to give us now 4 equivalent Sp3 hybrid orbitals in the nitrogen, one of which has already been filled, as we see in this case. So what does each of these bonds represent? Well, if we could kind of go back to our Lewis structure here, we'll just kind of redraw it, if you will. We'll call this bond over here, for example, call this guy bond number 1. So for example, this guy here from the nitrogen will then bond to a 1s orbital that is with hydrogen, right? And they would share those electrons. We'll call this guy number 2, which then can make a bond over here between the nitrogen and the 1s orbital there in hydrogen. And this, say, bond number 3, which again can make a bond with hydrogen's 1s orbital there. And that would represent the 3 bonds that we see between nitrogen and hydrogen. And we do have sort of 2 non-bonding electrons that are left over, and that would be represented by this hybrid orbital, which has 2 electrons in it, and that would represent the non-bonding electrons that would be there. So through this hybridization, it also accounts for the non-bonding electrons that we see in our Lewis structures. They sort of get filled through the process of sort of promoting up that electron. So you can get very specific in terms of talking about what type of bonds are happening. So for example, here we could say that the bonding that we see between nitrogen and hydrogen is the Sp3 hybrid orbital in nitrogen bonding to the 1s orbital in hydrogen. Hydrogen will not go through hybridization because it frankly has only 1 electron. So it will not hybridize, so it will just stay as a 1s orbital. Everything else can have sort of the ability to go through and sort of do hybridization, but hydrogen really will not. Any questions on that there? So this sort of theory here accounts for all the bonds that we see in NH3. It also accounts for all the non-bonding electrons that we also see in NH3 as well. Each of these, by the way, would be considered probably a sigma bond here between each of those. Those would be head-to-head sort of bonding that we would occur. So each of these sort of single bonds is where it will be more of a sigma bond, was sometimes referred to. That's the symbol for sigma, by the way. So if we take a look at water, for example, and sort of see the same sort of idea, if we take a look here at H2O, and once again, if we look at oxygen, which is 8, 1s2, 2s2, 2p4, it's got these 6 valence electrons. And we could look at water and the oxygen and count up our electron pairs. And once again, if we look at it, we see 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So once again, if you're not sure, this is just the best way to do hybridization. It's just to draw out these things like electron configuration and pretty much count up our electron pairs. Once again, 1s, 2, 3, and 4. So once again, we would predict that this guy would go through the oxygen here, would go through Sp3 hybridization is going to occur with it based on that. So if we look sort of what's happening and sort of what's accounting for all the bonding and non-bonding electrons that we see here, if we start with just our oxygen as sort of our orbital diagram for it, we have our 2s. And once again, here we have our 2p, which has 4 electrons to start with. Now, in this case, when we get that promotion of the electron like we've seen before, this guy is going to end up coming into this box, just like an orbital diagram, right? One at a time, then come back and pair up everybody. That is going to result in us ending up with something like this. And now that we see that we are going to hybridize the S in all 3 of those p orbitals, this once again will give us the 4 equivalent Sp3 hybrid orbitals that are going to happen here. And in this case, we will now have a situation that looks something like this. If we just look at our hybrid orbitals, and again, this is for oxygen. If we look at our hybrid orbitals, we see that 2 of the 4 are kind of filled already, right? Any orbital, even a hybrid orbital, can only hold 2 electrons. That allows only really for 2 bondings to occur with those guys there on the right-hand side. And that's okay because in water, obviously, we actually have only 2 bonds. We have a bond here and a bond here. Which once again can be done through a bond between the 1s orbital and a hydrogen. And same thing here, a 1s orbital here and this guy. And what we see is that would take care of all the bonds that we see. And we see through the hybridization process, we actually have a non-bonding pair of electrons, which would be represented by that hybrid orbital that came with 2 electrons through the hybridization process. And we have 1 more that already had the non-bonding electrons there in there. So we see very nicely that hybridization here does account for, all the bonds that we see in molecules, is also able to account for non-bonding electrons that we see in particular molecules as well. Any questions on that? Yes. Yeah, it is. So you absolutely, just like I did at the very beginning there, if you were asked sort of what is the hybridization of something, you could do it just strictly based off the Lewis structures, and you would count electron pairs, which is important for hybridization, the exact same way as you would do when you do geometry. So once again, if you happen to have some double bonds or triple bonds, you want to count those as only 1 electron pair. But that's exactly how you would do it. And again, it's related really to the electron pair geometry. And so this guy would be tetrahedral in sort of the electron pair geometry that would happen there with the 109.5. Okay. Yeah, so just so we're clear, this is just supposed to, on the bottom here, sort of help you understand where sort of all the bonds are happening and all the sort of non-bonding electrons are happening. But you absolutely could just draw a correct Lewis structure and count up the electron pairs and figure out the hybridization without obviously having to do the arrows or anything like that. Yeah. Any other questions on that? Okay. So again, this really nicely accounts for really what we do see in our Lewis structures and sort of the bonding that happens. And again, it can account for bonding electrons and also non-bonding electrons. Once again, these would be considered sigma bonds here, just single bonds where, again, the orbitals are basically just coming straight onto each other. Head-to-head overlap is what is sometimes referred to. So let's talk a little bit about some other things here. Whoops. Now, let's just say we had something where maybe we did have some double bond action sort of happening here. So let's say we had something like this. Just to show you sort of what is going on here. So in this particular example here, we have 2 carbons that are double bonded to themselves. And we also have our hydrogens that occur here. So what's going to happen when we get this to occur is we do have to do the geometry for each sort of central atom separate. So I'm just going to number these carbons here. I'll call the guy on the left carbon number 1, guy on the right carbon number 2, even though they're really kind of the same. So if we wanted to do our hybridization, we would look at each carbon sort of separately. And again, we could run through our just simply looking at it and our kind of orbitals here. So if we took carbon number 1 here and we wanted to count up the electron pairs around it, it has 1 electron pair. It has 2 electron pairs. And once again here, our double bond would count as only 1 electron pair. So it really has 3 electron pairs, which means if we just mark it off here, 1, 2, and 3, I'm doing an S and 2 Ps. So this carbon here, carbon number 1, would be Sp2 hybridized based off the Lewis structure that we drew there. If we look at carbon number 2, it actually in this case is identical. It's the same. So if we look at carbon number 2, it has 1 electron pair, 2 electron pairs, and once again, it is sharing that double bond in the middle, which would give it 3 electron pairs. And again, if you counted through it, 1, 2, and 3 would be, again, the Sp2 hybridization. First off, any questions on how to figure out the hybridization just from the Lewis structure there? Yeah. Okay, so if we want to see, what's going on in terms of our electrons and what's accounting for all the bonds and stuff that we see, we could go a little bit more into detail here and look at our sort of arrows and stuff like that. So if we look at our carbon, which would have 4 valence electrons, and it would look something like this, 3 and 4 in this case. Now, once again, this would be carbon 1 and really carbon 2. They're both the same, basically. This guy is going to promote up to that 2p empty spot there. And what that's going to give us is, again, an electron in each of these guys. And based on what we determined up there, we're going to go through Sp2 hybridization here, which means that we're going to take the s orbital and only 2 of the p orbitals, which, by the way, again, this is px, py, and that's going to leave us actually the pz not going through hybridization here. This is going to give us 1, 2, 3 Sp2 hybridization orbitals there. And I'm going to call this carbon number 1, which will have an electron in each of them. It will also leave us, though, one PZ unhybridized orbital that also has an electron in it. So that's sort of the hybridization that will occur for the carbon on the left. And since the carbon on the right is exactly the same, you'll get the same hybridization that will occur for the carbon on the right. So I'm just going to draw it next to it real quick here. First off, any question on that there? So this is really where all the electrons sort of end up in these hybrid orbitals, these unhybridized orbitals, as both of these guys go through hybridization. I'm just going to clear off a little bit up here, so I got a little bit more room to write. Okay, so redrawing our picture here so we can actually kind of see it one more time a little bit better. Okay, so if we want to sort of account for all of the bonds that we see, we can start with really the carbon and hydrogen bonds. So there's one here, right? There's one there on carbon number 1. So this carbon number 1 would bond to a hydrogen, making a bond. We'll call that one number 1. Carbon over here will also bond to another hydrogen, which is a 1s orbital that has an electron, making that second bond that occurs. On the other carbon on the right-hand side, we will have basically the same deal. We have the same sort of carbon and hydrogen bonding. So on the second carbon, it also will find itself bonding to a 1s orbital. And that will say bond number 3, and one more over here, which would be bond number 4. So that sort of bonding between the Sp2 hybrid orbital and carbon and the 1s orbital and the hydrogen accounts for the 4 sort of bonds that we see going on there. What is left really is the double bond, right? That is right there dead in the middle. Between the 2 carbons is basically the only bonds that we have left. And it is a double bond, which means, frankly, for a simple explanation, there's 2 lines, which means we need to make 2 bonds. We need to share some electrons. So the first type of bond, and by the way, all these bonds that we just made would be considered sigma bonds. So all these guys would be considered sigma bonds. Yeah. So the first thing that happens when we make a double bond is, frankly, the first line, if you want to think about it that way, it will actually be a sigma bond, just like all the other sort of bonds that we made. And that's going to occur from actually these 2 hybrid orbitals that are left over. It is these 2 guys right here that are going to come together to make that sigma bond that represents sort of like the first line that you draw for your double bond. At this point, we have used pretty much up all of our hybrid orbitals to do that. There's no hybrid orbitals left, but we still need to make one more bond for our double bond, right? Where's the only place we have electrons left? The unhybridized orbitals. So the double bond, if you will, the second line for the double bond actually comes from those unhybridized p orbitals, and they're going to overlap and make the second bond there in our double bond. Now, the sigma bonds result from those guys coming straight at each other, and you get the nicer overlap as they collide head-to-head overlap. And that's because, again, in this case, they're kind of similar in size. What we have going on here with our unhybridized p orbitals, which is actually our pz orbital, is, frankly, they are just regular p orbitals, these atomic orbitals, which have that figure 8 shape. And the way that these guys actually overlap is not head-to-head overlap where they just come straight at each other. They do what is referred to as side-to-side overlap. So these guys sort of overlap with the 2 lobes there on the figure 8s, and they do a side-to-side overlap. And when you get this sort of side-to-side overlap within sort of the plane of the bond here, which would be rounded around here, This is what is referred to as a pi bond. So this is what is referred to as a pi bond. And that is what's going to happen with these two. These two guys here are going to come together and they're going to overlap and make what is referred to as a pi bond, which is basically the second line that you see in a double bond. So actually a double bond is made up of two types of bonding. It's made up of first a sigma bond where the orbitals basically just head straight at each other and overlap head to head. The second sort of line of the double bond is made by side-to-side overlap of unhybridized p orbitals. And then that counts for all the bonds that we see here in this particular molecule. Any questions on that there? Now, if we had something that had sort of a triple bond, it would work kind of similar as well. So let's take a look at maybe what would happen in the triple bond situation. So we'll use our same carbons here, but we will do a triple bond between the carbons. So something like this. Once again, we'll kind of call the guy on the left carbon number 1, guy on the right carbon number 2. And if we wanted to, straight from our Lewis structure, which you absolutely could do without anything else, and figure out the hybridization, what would be the hybridization of carbon number 1? What do you think it should be? It is going to be sp. So once again, we would look at carbon number 1. It would have 1 electron pair. And once again, this triple bond would only count as 1 electron pair, just like what we do with geometry. And we would just mark it off. That's 2 electron pairs, and that is an S and a P hybridization. So we would expect this guy to hybridize sp. In this particular case, carbon number 2 is exactly the same. It has 1 electron pair. And once again, this guy is going to count as 1 electron pair. So that's 2 electron pairs, which means this guy will hybridize sp as well. First off, any questions on how to figure that one out there? Okay, so that obviously goes with our linear, sort of 180 degrees apart geometry there. So once again, we're dealing with the 4 valence electrons in carbon, and both of the carbons are the same. They have our 2 electrons there and our electron here. Once again, we're going to get that promotion up to that orbital there. Going to result in our 2p orbitals having 1 electron each, and our 2s having 1. And now that we know that it's sort of going to hybridize through sp hybridization, in this case, we're actually only going to take these 2 guys here to hybridize. And when those 2 guys hybridize, it is going to give us equivalent sp hybrid orbitals, which each have an electron. Now, in this particular case, the py and the pz orbital did not hybridize. So we will have 2 unhybridized orbitals that will each have an electron. And again, that's the py and pz orbital that's unhybridized. And this would be for carbon number 1. Now, carbon number 2 happens to be identical to it, so it would obviously have the same hybridization scheme. 2 hybridized orbitals here in p. And it will have its 2 hybrid orbitals here. It's sp. All right, and this would be obviously carbon number 2 there. All right. So once again, these arrows just to sort of show you where all the electrons are. And again, we're going to go through sort of the bonds here and identify where all the bonds come from. So let us do that here. Let's get some more room here. Erase some of that there. There we go. All right. So the very first thing that we could kind of look at, which might be easy, is the bonds between the carbons and the hydrogens, right? So what's going to happen in this case is we're going to take an sp hybrid orbital, and it's going to make a bond with the 1s orbital in hydrogen. And that would account for our number 1 bond there. That once again would be a sigma bond that's happening. We also have the exact same bond happening on the second carbon on the right. So this guy, for example, will come down and make a bond with our 1s orbital in hydrogen. That would account for our second bond that we see. Now, what's left here in this particular case is, frankly, just the triple bond action we got going on there in the center. And if I blow up our triple bond here, there we go. Much like the double bond, the very first bond that's going to happen is going to be a sigma bond. And that is, as we can see here, going to occur between the 2 carbons and their hybrid orbitals. So that first bond there would be a bond between the sp in one and the sp in the other orbital there. And that would make our sigma bond, which is sort of our first line there on our triple bond. Now, in this case, what is left is our unhybridized p orbitals. So we got, again, our py orbital or pz orbital on both sides. So these guys are going to do the sideways overlap. And in this case, we could get a pi bond that occurs, say, between these 2 guys, making a pi bond from the sideways overlap of these orbitals above and below. And then sort of in the other direction, we will also get our last bond there, which would be these guys coming together, our other p orbitals kind of coming together and making another pi bond because it is sideways overlap. So once again, our hybridization here accounts for all the bonds we see in our double, triple, single bonds. As you can see here, a triple bond is actually made up of a sigma bond and 2 pi bonds, resulting from basically sideways overlap of unhybridized p orbitals. And obviously, we know exactly what all of our bonds would be in this particular case. Any questions on that there? So hybridization does a really nice job of accounting for, all the sort of bonds and stuff that we see. Again, you will not be asked to draw any of these sort of arrows. You will need to be able to give the hybridization of atoms. But again, this is just supposed to show you where sort of all the electrons sort of end up and stuff like that. Any questions on that there? So frankly, if we had, something like this here, I'm just drawing letters now. All right. Well, why don't we do this? Let's do, for each of these guys here that have the red arrow, why not? Let's even do this guy here. For the red arrows, give the hybridization. And then secondly, how many total in the entire thing sigma bonds are there, and how many pi bonds are there in the whole entire molecule. So take a moment and figure all that out. Okay, let's take a look. So we're going to start with hybridization. So we'll start with the guy on the left here. We want to count up electron pairs just like we would do with geometry. So obviously this is 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So frankly, you could just do this, always start at S, go 1, 2, 3, and 4. So this guy should be Sp3 hybridization. Any questions on that one there? Coming to the carbon to the right there, once again, we're going to count electron pairs like normal. This would be 1 electron pair, 2 electron pairs. Now this double bond will only count as one electron pair, just like we do with geometry. So for this guy, it would be 1, 2, and only 3 there. And this guy should be Sp2 hybridized in this case. Again, double bond counts as only a single electron pair. Any questions on that one there? Coming to our guy to the right of it, has 1 electron pair, 2 electron pairs, and much like the guy to the left there, our double bond here will count as only 1 electron pair. So again, if we start at the bottom, 1, 2, and 3 total electron pairs, this guy will also be Sp2 hybridized. Any question on that one there? Coming to the carbon at the end there, it has 1 electron pair, 2 electron pairs, and once again, our double bond will only count as 1. So that's 3 electron pairs, which will end up the same. 1, 2, and 3. In this case, would be an S and 2 Ps. Any questions on that there? So you can apply hybridization to central atoms. You can also, if you wanted to, apply hybridization to atoms on the outside, like our oxygen here. And we would do the same thing. We would count up electron pairs around the oxygen. So that is 1 electron pair. That is 2 electron pairs. And again, the double bond here would count as only 1 as well. So that is 3 electron pairs, which once again takes us to basically the same deal. Sp2 hybridization. Any questions on how to assign hybridization here? So you could clearly see, again, you don't need to do all the arrows to show where everything went, but you could just do it simply based off a good Lewis structure and counting electron pairs like we do with geometry. All right, so then we want to know in this case how many sigma bonds there are in the entire thing and how many pi bonds there are in the entire thing. So let us go through and sort of add those up. Every pretty much single bond is a sigma bond. So this would be a sigma bond there. This would be a sigma bond there. That's 2. That is 3. That is 4. That is 5. That is 6. That is 7. That is 8. Remember that also a double bond is made up of a sigma bond and a pi bond, which means there's also a sigma bond here and here as well. So that would be, I lost track there, 2, 4, 6, 8, 10 total sigma bonds, I think, in this entire molecule. A pi bond is really kind of the second line to make the double bond or the third line to make the triple bond. So in this case, we don't have any triple bonds, but we do have a couple of double bonds happening. So this would be a pi bond here, and that would be a pi bond there. So that looks like 2 would be a winner on that one. Any questions on how to assign hybridization, sigma bonds, pi bonds? Yeah. There really won't be, because as we saw when I did all the arrows, you know, really what's left over at the point where you're going to make a double bond or a triple bond is those unhybridized p orbitals. And because they're unhybridized, the only way they could kind of overlap with each other, because they kind of make that figure 8, is through that sideways overlap. So it always will typically be pi bonds. The reason really sort of the first line in the double bond or the sort of first line in the triple bond is really a sigma bond, is because typically what you have left is a hybrid orbital that's left over on each side, and they're able to sort of come straight at each other because they're kind of on the same energy level and they're the same shape, so they come really at each other pretty easily. But that's always the key. So pretty much a single bond is a sigma bond, double bond, sigma, and then pi. And again, a triple bond would be a sigma, a pi, and a pi. And again, all the pi orbitals there, all the pi bonds there should really come from those unhybridized guys. Other questions? Okay. All right. We kind of jumped ahead of some of these slides here. So I think we went through NH3 here. We just did our multiple bonds. Again, like I mentioned, the pi bond is that sideways overlap, and that is the difference between a sigma bond, technically speaking, which is they just run straight into each other, and really a pi bond, which is usually from these unhybridized p orbitals, where they again do what is referred to as sideways overlap. Sort of above and below the plane of the bond that happens. This is head-to-head overlap. When you have a triple bond, again, you got kind of like the, and I'm not the greatest artist here, but you know, you got kind of like the two p orbitals happening, where we get sort of that sideways overlap happening in each of those cases. To make that triple bond. Okay, so I think we talked about those. Now let's talk about expanded octets. You can have expanded octets that do get into the d orbitals, if you will. So if we do our little kind of quick way of figuring out hybridization like this. Once again, as we talked about, hybridization is related to the electron pair geometry. So when we talk about electron pairs, we have two electron pairs. The electron pair geometry is going to be our linear and is going to be hybridized as Sp. When we have our three electron pairs, that's going to be trigonal planar electron pair geometry, which would hybridize Sp2. Our four electron pairs would be tetrahedral, which would hybridize Sp3. And remember that we talked about all those geometries and the expanded octet, which has us to, for example, 5 electron pairs, which is our triangular bipyramidal. Now, if we just do our counting of 5 electron pairs, we would start here, 1, 2, 3, 4, and 5. And if we keep track of everything there, that is an S, that is 3 Ps, and now we have gotten into the d orbitals. So the hybridization for something that is triangular bipyramidal would be Sp3d. Again, just really counting up the electron pairs. And we also had 6 electron pairs, which is octahedral, which would be 6 electron pairs. So 1, 2, 3, 4, 5, and 6. And that would then be an S, 3 Ps, and 2 D. So that is Sp3D2 hybridization that does occur. So, like I said, just strictly drawing your Lewis structures, counting up the electron pairs like you would do geometry, and you could just mark it off on this chart on the right, and you should be able to hit any hybridizations you want. That's pretty much as far as we would go, obviously, in terms of hybridization. Any questions on that there? Yeah. Yeah, so the deal with diatomic, for example, so most of this and like really this type of geometry, right, is for 3 or more atoms, really. You know, and that's because you then would have sort of a central atom that happens that gives you sort of that geometry that happens. Really in sort of a diatomic molecule, there's really not necessarily a central atom. You could still sort of do it for it if you want, but it pretty much will always come out as linear, basically, for the most part, because it's just going to be 2, no matter if you had something like that, or you know, or actually it won't always come out linear, but you know, you could, I guess, apply hybridization for this guy and it would come out as Sp2, but usually we don't apply sort of hybridization to something that's diatomic unless you want to do it like something like that, where you just got to take one or the other sort of side, since there's not really a sort of essential atom. So, but if you did for this guy, this technically that nitrogen would be Sp, and this guy actually would be Sp2, since there's obviously 3 in there. Other questions on that? All right, so obviously you need to be able to draw Lewis structures. You need to be able to identify the electron pair geometry, the molecular geometry. You need to be able, obviously, to identify the hybridization like we just did, and obviously sigma bonds, pi bonds, and all that kind of stuff. Any questions on any of that stuff there? Okay, we're going to kind of finish up here talking about really molecular polarity. So we talked about bond polarity sort of earlier. And bond polarity is when we use that difference in electronegativity values. And remember, bond polarity really just kind of tells us, if we do sort of use electronegativity, that between these two particular atoms, would we expect, again, those electrons to be shared equally or unequally? And as I mentioned, I think in the last chapter, there's really only one place where that really does tie over to molecular polarity, and it actually is in those diatomic molecules. And that's really because there's only really one bond present in the entire molecule. Now, if something is a polar molecule, it will have what is known as a dipole moment. And a dipole moment is taken into account overall the molecule. You know, is there a spot of the molecule where there's really a lot more electrons sort of hanging out? So there's a higher sort of electron density happening in a particular location than in another. You know, if something does have a dipole moment, it is also sometimes represented with the same sort of dipole arrow that we saw when we talked about bond polarity, except that for the molecule, for example, we'll just draw a circle for the molecule here. If we had sort of a dipole moment heading in this direction, what this would tell us is kind of the top part of this molecule is more negative. So there's much more electrons hanging out up here on the top than obviously on this part, which would be more positive. And basically that is what a polar molecule is. There is basically a side that is more positive and a side that is more negative in that molecule as a whole, as a result of really unequal sharing of electrons as a whole, where electrons sort of migrate to one side of the molecule versus the other. And it's sort of a fixed separation that occurs when you have a polar molecule. No matter what the situation is, they're not going to go back and forth or anything like that. They're pretty much going to be locked into place on that side of the molecule. Now, polar molecules will have a dipole moment. Non-polar molecules will not have a dipole moment. And basically what that means is if you have a non-polar molecule, what we're basically saying is overall in that particular molecule, taking into account all the bonds that are present, there's sort of overall equal distribution of electrons around the entire thing. So what that means is you kind of get like a neutral molecule, if you will. There's not a side that's more positive. There's not a side that's a little bit more negative, because the electrons are pretty much evenly distributed over the entire molecule. So for lack of a better description, really you get something with like no charge sort of happening, as opposed to a polar molecule, where you do definitely have a side that is more positive and a side that's more negative due to these unequal distribution of those electrons over the entire molecule. Any questions on that? This, by the way, is the distance between them and just the radius and also the charge. We're not going to actually calculate the dipole moment, but you could calculate the dipole moment. It's sometimes given in what's referred to as a Debye, and we won't basically calculate or anything like that. So let's talk about, frankly, the simplest molecules to determine whether or not something is going to be a polar molecule or a non-polar molecule. And that is really those diatomic molecules. So something like our F2 that we saw, you know, something like our O2, these are what are referred to as homonuclear diatomic molecules. Homonuclear, like a homogeneous mixture, means the same. So it's the same elements basically involved. And because those basically are the same elements, we could look first at the bond polarity here. And would we expect these bonds here to be polar or non-polar in this case? We would expect, because the electronegativity, right, is 4 and 4, the difference would be 0, that both of these guys would possess really a non-polar bond. Same thing with oxygen. They obviously both would have the exact same electronegativity value, which would give you a difference of 0 and should be nonpolar. So what we just technically calculated using the electronegativity is the bond polarity here, which tells us that these are nonpolar bonds. This also does relate to molecular polarity in this case, because when we look at each of those guys, there frankly is just one bond present. So because there's only one bond present, and that one bond is a nonpolar bond, in addition to that being a nonpolar bond, that would make this guy a nonpolar molecule. Same thing here with our oxygen. There's only one bond present. That is a nonpolar bond, which means O2 should be a nonpolar molecule. Any questions on that there? Now, if we have a diatomic molecule where they are not the same, like HCl, maybe HF, this is going to lead to a polar bond when we look at these guys, right? And if we look at this bond here and we take some difference in electronegativity of like 3 minus 2.1 gives us 0.9, gives us a polar bond that's going to happen. We could draw our bond dipole arrow heading in this direction, right? That means that the chlorine side should be more electronegative than the hydrogen side. And because this bond is a polar bond, and we would have the exact same situation happening over here, the fluorine is much more electronegative. 4 minus 2.1 gives us 1.9 difference in terms of electronegativity, would give us also a polar bond with this guy as well. Now, kind of the same reasoning as above, since that is the absolute only bond that we see in this entire molecule, and it happens to be polar, each of these guys would actually be a polar molecule. Where the chlorine side in the first guy, the fluorine side in the second guy would actually be the more negative side of that molecule, because that's where the electrons are hanging out. If you drew like a blob circle of it, this side would be more negative, this side would be more positive because of that unequal sharing of electrons over the entire molecule. So diatomic molecules are really the simplest ones to figure out whether or not the molecule is polar or not. And it's basically dependent on the bond. So if that bond is polar, the entire molecule will be polar. If that bond is nonpolar, then the entire molecule will be nonpolar. It doesn't matter, as you can see there with the oxygen, if it's a double bond, triple bond, it doesn't matter. Again, you're just looking at that individual bond. Is it going to be polar or nonpolar? So this is really the only place in polarity where both bond polarity and molecular polarity are basically the same, because there's only one bond in the entire thing. Any questions on that? Now, if everything was that simple, that would be great, but it is not, of course. So when we do get to molecules that have 3 or more atoms, there's actually a couple of different things that you actually need to look at to determine whether or not something is going to be polar or nonpolar. So let me actually go with this. So when we have 3 or more atoms, you have to look at 2 things. You first have to look at, is there polar bonds? So clearly, if that answer is no, there is no polar bonds, you're pretty much done. That molecule is going to be a nonpolar molecule. If you do answer yes to this question, that there are polar bonds, you then have to look at the second thing when you have 3 or more atoms, and that is the molecular polarity. Not the molecular polarity, I'm sorry. That is the molecular geometry to help you decide the molecular polarity. So you do have to look at the molecular geometry. And depending on the geometry, it may or may not cause the molecule to be polar or nonpolar. So let us take a look at this. Actually, let's go this way to find somewhere right here. I think I had. There you go. Borrow this. So let's say, for example, here we had something like our good friend CO2. Right? which we drew earlier, I think, as well. So that's carbon dioxide. So the first thing that we would want to look at, obviously, in this case is we definitely have 3 or more atoms. So we want to determine, is there polar bonds in this particular molecule? Is there polar bonds in this molecule? Is the bond between carbon and oxygen, is it polar or non-polar? What do you think? It is polar, and again, we can use electronegativity. We actually don't need the numbers. If we look at the periodic table, carbon and oxygen are in the same period. Oxygen is further to the right, which means it should be more electronegative, and that means that we should result in a polar bond. And we could draw our bond dipole arrows heading in this direction. We could also draw one for the other carbon to oxygen heading in this direction, again pointing to the one that is more electronegative. So in this particular case, the answer is yes, we do have polar bonds, right? So you may think it has polar bonds, so it would sort of make sense that the thing should be polar, right? Since frankly, if we look at this, every single bond in that molecule is polar. But this is why it's really important to look not only at is there polar bonds, but also the molecular geometry. What would be the molecular geometry of this guy? It has 1 and 2 electron pairs, and it has 2 bonds, which means it is going to be linear is the geometry of that with 2 electron pairs. Again, each double bond counts as 1 electron pair, and each double bond counts as 1 bond each. So that's 2 electron pairs and 2 bonds, which would give us our linear molecular geometry. So this guy is basically a straight line, which means if we look at it, this is basically CO2. And we basically have an oxygen pulling this way, right? But we do have the oxygen pulling the other way. I am actually pulling in both directions. Is my pen going anywhere? My pen is not going anywhere. So in this particular case, because CO2's geometry is linear, those bond dipoles essentially will cancel each other out. And although it does have polar bonds, these guys will make this guy a non-polar molecule because of the geometry of it. Any questions on that? That is because these guys here, which are the bond dipoles, they are what we like to refer to, I think, in physics as vectors. Vectors have direction, they have magnitude. Then I fell asleep. But I woke up long enough to remember in certain cases, they do add to each other. In other cases, they do cancel each other. So typically, if you got vectors heading in equal and opposite directions, they cancel, right? Or if they're heading right at each other, they cancel. Like kind of 2 people pulling a rope, right? Not going to go anywhere. People pushing a door on opposite sides, right? It's not going to go anywhere, right? So they kind of cancel each other out. If you end up with sort of guys heading in opposite directions, not equal and opposite of each other, they typically will, like a tug of war, right? If you get like 3 people on one side pulling, right, and one guy's like trying to hang on, right, it's going to kind of pull the guy away. You will end up with a polar molecule. So CO2 is a really good example that demonstrates you could definitely have polar bonds within the molecule, but because of the geometry, they actually may cancel each other out. So if we look at something like water here, which is our favorite, we would want to do the same sort of approach. Is the bond between hydrogen and oxygen polar or non-polar? It is polar, oxygen being more electronegative, heading in this direction. And we would also have one that is heading in this direction as well. So just like above in water, we do have polar bonds. We do want to look at the geometry here. What is the molecular geometry of water? Has how many electron pairs here around the oxygen? Anyone? 4, thank you. And bonds, it has 2 bonds, yes. So something with 4 electron pairs is tetrahedral for electron pair geometry. The molecular geometry, though, with 2 bonds is bent or V-shaped, yes. And that's why water is always drawn, as we talked about, kind of like in this shape. So in this particular case, what we got going on here is we got sort of water like this, and we got the polar guys going this way. They're sort of meeting at the top, if you will. If you imagine you kind of pull from the top, the whole thing will kind of come up. And we actually get a net dipole moment that happens with water heading in this direction because they actually add to each other, where the oxygen is more negative. The oxygen is more negative. The hydrogen part is more positive. And that is our dipole moment. And this would be a polar molecule in this particular case. How does that work? It really works like this. You take the vector heading in this direction. Then you take the other one, kind of point to tail type of deal. And in this case, they add to each other heading in that direction. Now I'm really physicsed out right there. That's all the physics I got. But they add to each other in that direction, and that's why it heads in that direction. They sort of cross like this, and then they add in that direction. So you definitely can have polar bonds within a molecule that results in a non-polar molecule because of the geometry, and vice versa. You obviously can have polar bonds in the molecule that results obviously in a polar molecule as well. Any questions on that? Frankly speaking, nobody wants to draw vectors and figure those things out. So there's a lot of times a very easy way that you could do it, and there is what is sometimes referred to as symmetrical geometries and sort of unsymmetrical geometries. And symmetrical geometries are things like, and these are molecular geometries that we're talking about here. This is something like your trigonal planar, your tetrahedral, your triangular bipyramidal, your octahedral. What most of all these guys have in common is if you draw the Lewis structure, there are no lone pairs on the central atom. So on the central atom, if you draw it, there's no dots, basically. They're all bonded electrons. And if you have this situation and all the outside atoms are the same, it typically will result in a non-polar molecule. That is because in all these geometries, everybody ends up equal and opposites of each other. So if all the atoms on the outside are the same, they're all going to be pulling or pushing the same, and they will essentially cancel each other out. So if I took something like this guy here, I won't draw all the dots around the fluorine, but there are dots around the fluorine. Between carbon and fluorine, fluorine is more electronegative, which means we do have polar bonds all heading towards the fluorine. But in this case, when I look at the Lewis structure here, I see no dots on the central atom. I see everybody on the outside. They're all going to end up equal and opposite of each other, kind of like everybody pulling on the rope, equal and opposite of each other. They're going to all cancel out, and this would be a non-polar molecule. Now, the exception to that is if you have no dots on your Lewis structure, but everything on the outside is not the same atom or same element. It will then become a polar molecule. So to show you that, we can take our same guy here, and if we swap out, and again, I'm not going to draw all the dots on the fluorine, but if we swap out a fluorine for a hydrogen in this particular case, what's going to happen is we're going to get the polar bond heading to the fluorine. And the carbon-hydrogen bond is actually nonpolar. and slightly heading towards carbon. It's actually a little bit more electronegative. So what we end up having in this case is like 3 guys pulling on the rope, right? And 1 guy not really pulling, right? So you can imagine he's going to be dragged across. And we would get a net dipole moment heading towards the fluorine. And this guy would then become a polar molecule. So if you have any of these sort of symmetrical molecular geometries where you basically draw your Lewis structure, no dots, everything on the outside is the same, going to be nonpolar. You draw your Lewis structure, no dots, everything on the outside not the same, probably going to be a polar molecule as a result of that. Any questions on that there? Now, some unsymmetrical geometries. And again, these are molecular geometries. This is going to be your trigonal pyramid, your angular, your bent or V-shaped, your, trying to remember all of them there, T-shaped, I think we did, your seesaw, your square pyramid, got most of them, I think. But these are basically, when you draw your Lewis structure, you will see dots, or lone pairs on the central atom. And if you draw your Lewis structure, you see dots or lone pairs on your central atom, and everything on the outside the same, it is going to be most likely a polar molecule. For example, like the water there. I see dots on the central atom. I see everything on the outside is the same. It's going to be polar. NH3. I see dots on the central atom. Everything on the outside is the same. It's going to be a polar molecule. So that's a really quick way that you could kind of do it. Pretty much if you got dots on the central atom, everybody on the outside is the same, or really even dots, and everybody on the outside is not the same. It most likely will be a polar molecule. If you draw Lewis structure and you have no dots on the central atom, then it will be a nonpolar molecule if everything on the outside is the same. There are a couple of exceptions that where you could technically get dots on the central atom and still have a nonpolar molecule, and that would be in a couple of those expanded octets. And that is the linear that's expanded, where you have basically the bond like this, and then you got like the non-bonding electrons happening, kind of like that. So the expanded linear, because it's linear, it's 180 degrees, you know, it could be a polar molecule if you have, it will be non-polar molecule because you have basically the same thing on the outside. So if these guys are the same element, you will end up with a non-polar molecule because, again, it's a straight line pulling opposites of each other. The other one is the square planar, and that is also your expanded octet. And that is the one where we end up with really the square geometry with the dots happening on the other side. And again, if all these guys are basically the same element, they're going to basically be on the corners of a square, right? And they're going to pull equal and opposite of each other and will cancel each other out. So those are sort of the 2 exceptions where you potentially could have dots on the central atom and end up with a nonpolar molecule. Otherwise, pretty much it will be polar. The one thing that you really have to look at is the straight linear, the regular linear, the 2 and 2, because in a 2 and 2 linear, you could have, like we talked about with CO2, they go opposite and cancel. They could go at each other and cancel, but you could have in a linear situation where they're all heading in the same direction in terms of electronegativity, and that would then make it polar if they're all kind of heading to the right there. So this is a really quick way that you can determine molecular polarity based on your Lewis structure, kind of like dots, no dots, and what's attached there. And I would say probably 9 times out of 10, you would be probably correct in your assessment by just doing it that way. Any questions on molecular polarity? So there's one topic in this chapter 4 that we're not going to talk about, which is molecular orbital theory, because I don't want to, so we're not going to do that. So it is in that chapter, so you're not responsible for molecular orbital theory, but you are responsible obviously for hybridization, and obviously being able to determine is the molecule polar or non-polar. Any questions on that? We're going to quiz on all this stuff here next Wednesday. Lewis structures, everything in bonding, basically everything in chapter 3 and 4. So all the bonding stuff that goes together. So ionic bonding, covalent bonding, drawing Lewis structures, geometry, polarity, all that kind of stuff. I will do it at the start of lecture on Wednesday, I think. Yeah. Any questions? All right, this should wrap chapter 4.